Hello and welcome to this video manual for my Computing for AI module, Assessment 1. This will be submitted as part of Assessment 2. My name is Shivam Garg. In today's video description, I will talk you through the selection of my dataset as well as all the code that I'm running through it. So let's get started. You will find that I have used Jupyter Notebook for my code. The first step of my exercise has been to break down the process into 8 different steps, starting with an explanation of the dataset leading to a final target field. In the description of this video down below, you will find some timestamps with minute and second to each step. So if you want to jump between them, by all means, go ahead. Moving on, the first step, looking at the dataset. This has been sourced from Kaggle, as you can see. This is a BIM AI integrated dataset. Now, what is BIM? BIM means Building Information Modeling. Just like when you buy a product, you have a whole bunch of information associated with it, warranties, product costs, this, that, the other. In the same way, in construction, when we build buildings, we have a whole lot of data associated with the digital model of the building, as well as the process of building it and the costs and whatnot. All this can be used to make informed decisions about the life cycle of the buildings and how to manage its life cycle. And that's what this data set covers. It goes into a fair amount of detail. This data set is captured in America across 1,000 different buildings, 5 American cities, and 5 different building types, primarily public infrastructure. In my code, I cover the descriptions of the 28 different fields for this data set. So even though you can see them within the Excel spreadsheet, I have explained what each field stands for and what it means within the step 1 of the data set. The process would be to first break these down and assess the relationship between the fields. Now, with such a large data set and so much information, what I have done is classified them into 7 analytical categories to first understand the quality of information that I have been given. And then this will lead to 3 different target fields. That's structural stability, cost, and risk. And I will be doing prediction, classification, and regression across these fields. So the first analytical category is financial data, which involves costs, plan cost, actual cost, cost overruns. These are all fields of the data set that I'm going to be explaining in this, but I'm skipping past that so we can just cover them here. Scheduling data, which means planned duration of the project, actual duration, and schedule deviation basically means delay, how much time got wasted. Structural health data, which means vibration level. That's effectively when a building is constructed and it undergoes seismic loads or wind loads, it can obtain some degree of vibration. There's always a tolerance for that. It's only in millimeters, it's very, very minute, but it's always there. It's for the health of the building. Crack widths, well, every building develops some cracks. Most of the time, they're very normal. They are in millimeters. They're not detrimental most of the time, but they have to be recorded. And load-bearing capacity, how much load can a building take? Environmental data, temperature, humidity, weather conditions, fairly straightforward. And air quality index, very important. Resource management, again, very important when you're constructing a building. How much material was used? What was the energy consumption? Well, how much time was used by way of labor hours? And how much equipment utilization was recorded? And then drone data for analysis of the final product. And risk data, very important. The idea is to minimize risk as much as possible. So the first step after doing all this in this exercise, it's step 2, is importing the machine learning algorithms. Now you're asking yourselves, what is this? Machine learning algorithms are pieces of code that have been written in advance, vaguely describing them, and they can be used to conduct very complicated processes fairly straightforward and very easily. We have a large wealth of machine learning algorithms that have been designed and ingratiated as part of the Python community. For the purpose of this exercise, I'm going to use matplotlib, which is for static visualizations, plotly for interactive visualizations, Seaborn for, again, heat maps, box plots, pandas for importing my Excel file, among other things, and NumPy for cleaning and transformation, as well as scikit-learn for a whole bunch of different regression, classification, scaling, k-means, PCA, linear regression. We'll cover all of this as I go through the bodies of the code. So I've imported all these algorithms. You'll find that in the code that I've submitted, all the results have been shown. So I'm just going to run through those now. In my submission, you will discover that I have structured all the code in an OOP fashion. That's object-oriented programming. So all the steps have been curated like classes. And then within those classes, there are separate methods that conduct the function. At the end of the class, I create an instance and I invoke the method to conduct the function. That's the standard through which I have written all the code in this submission. The first step is always the constructor, usually used to define the variable, in this case .data, which contains the data set. I often think of it as the sort of localized version of the data variable that works within the definition of the class. So in this instance, for dataset import, that's the name of the class, we've got the constructor, and then we define the name of the dataset, the address effectively, in a survey variable. And then I set up an exception handling. So if the user encounters some errors, instead of Python giving them a large pink box with a whole bunch of different code, Python will give them a more tailored result to explain to them exactly the mistake that they made, or near enough to it. So it's a bit more user-friendly to provide try, except, exception handling. So I've done that here. Self.data will contain will import the dataset using pd.readexcel. This is a pandas command. I've used readexcel because in my dataset I have done some formatting to make sure that when you open it, you can see the headings clearly, you can see the numbers clearly, and saved it as an Excel file. That's why it's importing it as an Excel. Runs a bunch of different exceptions. In this instance, thankfully, there's no problem. We've got the dataset and the Jupyter Notebook saved in the exact same location, which is very important. And that's why when it imports, it looks something like this. So you have the message that needs to print here, dataset loaded successfully, which it prints. And then you can see my dataset. It's got 1,000 different rows, as I said, and 28 different columns or fields. Now, moving on to EDA, which is exploratory data analysis. This involves pre-processing, cleaning, and a bit of analysis of the data, initially sort of visceral look of the data. Again, set it in the class data pre-processing. I've got different functions doing different preliminary methods, or different methods doing preliminary functions, like looking at the shape of the data set, looking at column information, printing of the head, describing what the data set is. So anyone taking first glance at it can get a very clear information of what the data set is. Important though here is these two methods. One is that removes any extra spaces and null values from my data set. So if there's any fields that have been provided with zero values or null values, not zero, but null values, that can be removed, and any extra trailing spaces can be cleaned out, so it becomes a nice tight set of information. Checks for missing values as well and returns the data set. And then again, within this, removes any large decimal places. So you'll find in the dataset some of them, for example, cost really have or duration have about 7 or 8 different decimal places. We don't really need that. We really don't. It can be shortened to about 2 decimal places. So that's what this does. You'll find that it accepts the self.data and then returns self.data. So it keeps everything within the localized self.data framework, but it returns it at the end of the function, which is important. So it keeps everything or does everything to the same data set. At the end of the class, I invoke all these functions, and just as expected, you get to see all these different prints of how the data set looks, preliminary understanding of the data set. As part of pre-processing, as part of EDA, I also print the clean data and histogram it to understand how every field relates to the rest of the data set, how it functions, what its range is. Again, we invoke these functions, and you see, as you can see, the decimal places have been rounded off. You see some data set column information because we did include that as part of one of our methods. And then you see some histogramming, so end date, schedule deviation, every field, it shows its performance effectively. And lastly, or third, out of 4 steps. Here we do a little bit of analysis of the data set. So we have 5 different types of buildings and we have 5 different cities. So I've taken something like cost, which seems to be paramount when it comes to building construction, and analyzed it, or sort of expressed it in relation to the different types of buildings and the different types of cities. You'll find that the class and method framework structuring for both these 4.3 and 4.4 is exactly the same, but the function output is slightly different. So here we have the prototypes of the buildings set out, and I create a heat map and a combined scatter plot of the planned cost versus actual cost, showing us how these buildings are performing. And the fantastic thing is that I have used Plotly. So you'll find px.scatter, that function there, that's a Plotly function. And what that does is it gives me an interactive result. So when I hover over these dots, for example, the blue dot here is for tunnel. If I hover over that, I can see all the tunnel information. If I hover over bridge, I can see all the bridge information. And for someone who's new to the dataset or just looking at it, it's fantastic to see the range that it covers between cost and get a feel for all the information that is available. Same with the heat maps. You can see the correlation between the different fields. A very similar structure, like I said before, but with cities. For the 5 cities, I've set it up to create a heat map. It selects the data types, defines the size of the map, and then SNS, which is a seaborne function, creates the heat map with the correlation factors. And this is effectively like a color prototype. So you'll find that when you look at different visualizations, you can select different prototypes. And I've tried to keep them different between different functions so we can tell the difference. Same for combined scatter plots, planned cost, actual cost versus location. So you'll find that here it's happening on the basis of cities, and then you can see a combined heat map. This was step 4, which was EDA. Now let's look at the dataset field assessments. Like I said before, I have divided this, I've structured this exercise into 7 analytical fields, 7 analytical sections which look at correlated fields. So when we're looking at financial data, it illustrates the trend in spending from the actual versus proposed over a period of 5 years, which is the duration of this data set. And I felt that the best way to do it was by using an S-curve. So quite simply put, I have used a pandas function here to convert. So this is a class comparing costs with a constructor, as usual, assigning a data set to self.data, and we do all the work on self.data. And then, so we're not making any changes to the data set as such, we're just analyzing it. We correct the date format in case it's set to an American format. We want to convert it to a British format so we can work well with it. We sort out we isolate the end date from the data set. We calculate the total actual cost, the total planned cost. That comes as a function for calculating the total costs. Fairly straightforward, as you can see. And then we use matplotlib PLT, which is used for static visualizations, as I said, define the figure size, and then define the line properties so we can tell the difference between both of them, customize the display types, and it invokes functions, and this is it, right? So as you can see that from 2020 to 2025, there has been a very sharp increase in both actual and planned costs, right? Planned costs are here, actual costs are here. So actual costs are higher and significantly higher. There seems to be stabilizing here, but they're quite a bit high. So this can be a cause for alarm for anyone looking at this data set and think, oh, you know what, we need to worry about this. Also, you will find in my submission at the end of every analytical step and every step that I've taken, I have provided a conclusion field that summarizes the takeaways or the key takeaways from that exercise. So hopefully that's useful. Moving on to schedule deviation versus planned against actual duration. Again, we're looking at time as a resource. You know, there's a planned duration for a project, and then there's actually how much time you spent on it. Okay. And schedule deviation is effectively the time wasted or the extra time that we spent, which can have detrimental effects because that's that much more labor, that much more resource, what have you. So we're looking at schedule deviation, and I've decided to do this as an interactive scatter plot. And I'll show you that in a second. So X is planned duration, Y is actual duration, all set in a class schedule deviation with a constructor and an int plot function or method, sorry. When I say function inside a class, it is a method, you know. Hover data, I want to see all the column information when I hover over these dots. That's why this field is important. And the color, here is the schedule deviation. So the schedule deviation will color the dots differently, and that's how we'll be able to tell the difference. I set the labels and the title, the template, and then add some more plot properties. This means that it will show a schedule deviation legend text and show the legend, as that's why it's set to true. Width and height for the map, and then we show it and return the data. So we've taken the data and we return the data. This is it, right? So you can see the gradient is darkest at the bottom and highest or lightest where the schedule deviation is higher. And this particular gradient, I really like this because it shows a very clear indication of where there's been the most amount of wasted time or most amount of extra spent time versus the least amount of the least amount of extra spent time, versus the highest. The least is at the bottom, which is the darkest, and the highest is at the top when it's lightest. And it seems to be all moving up towards this corner, the top right hand corner of the map. That's why this I've used this as a scatter plot, so it plots every single job on this as an interactive scatter plot. You can see how every project has been performing, which is very useful when you're looking at such a large, rich data set. Moving on to structural health data, I mean, it goes without saying that when you're building buildings, you want them to be structurally stable, you want them to have good structural health. So it's important to understand how they're performing. I've analyzed this through a k-means cluster, and I'm going to show you that why. I have isolated the structural factors in a list, created a class structural health monitoring, set out a constructor with the structural factors localized variable and self.data localized variable, and then isolated struct.data as a local data frame. Okay, so we're not making changes to the main data frame, just the local one, and only included the structural data in this data frame. So data involving these fields, right? Now, within this, we are selecting the numeric columns using the select D types and the number field. So any field that only has a numeric data type gets stored in numeric columns, and then transform it to standard scalar. What does standard scalar mean? You'll find that I've used this function quite a lot, and we defined it earlier when we were looking at the machine learning algorithms as part of a scikit-learn import. What is standard scalar? When you look at my data set, you'll find that some fields have smaller values, like 699, for example, for plan duration. And then the cost overrun goes in a couple of million, right? If I don't provide a level playing field for these different fields when they're coming together, the fields which have larger numeric value, forget about the unit for a second, larger numeric value are just going to dominate the fields that have smaller numeric value. That's not helpful. So in order to make sure that we have a sort of level playing field, we use this function called a standard scalar, and it brings everything within, it scales everything to the same unit base, which is useful when you're then analyzing that. And then applying preprocessing, which saved in x.preprocessed. So we fit transform this structural data to a numeric transformer, apply preprocessing to it. K-means clustering, a fantastic function to see the mapping of different fields. In this case, we use 3 clusters. Why? Because we've got 3 different structural factors, and we want to see the overlap between them. Random state is usually how many different, how much level you want to go into it, and this seems to be the standard we use. We fit the k-means to the preprocessed data and saved it into clusters, and then create a new column called cluster and saves this information to the data frame. And then finally use PCA to define the dimensions of the map and transform this into a 2-dimensional coordinate graph. We specify the plot size, specify the zeros and ones, that if it's 0, 1 and 2, it's usually 3 dimensions. 0 and 1 means 2 dimensions. We provide the cluster field, which remember we did here, where we saved clusters into the new field called cluster for structured data. Clusters was the preprocessed information from k-means. Specified a CMap. This is effectively a color palette. and define the labels, and here we go. When we invoke this function, this is what we get. We print it and cluster it by 3 different properties, okay? And we provide the mean of these properties. So 0 at the bottom, that's the darkest, that's these values, that's the 0 cluster, and then 2, which is the lightest, is over here. What I find interesting in this cluster is that the 3 clusters don't have any common Venn diagram. They don't have a common Venn map. They have overlaps intermediary between the clusters. So the green and the yellow have an overlap, and the yellow and the purple have an overlap, but the green and the purple don't. And the 3 don't have an overlap between them. This is important to understand the relatability between structural fields. So even though they are correlated, they are not, this correlation doesn't tantamount to causation. That's one thing that I can specify quite clearly looking at the way this map has turned out. Okay, moving on to environmental data. Now, in my data set, we have a field called weather conditions. And it's somewhere here. Where is it? Where is it? Here we go. Weather conditions. And it says different fields: snowy, rainy, cloudy, stormy, sunny, 5 different kinds of weather conditions. What I have done here is, in order to make them more malleable and usable for my analysis, I have used one-hot encoding. Effectively, what that means is that you convert that into a binary numeric format. So I use the value counts that shows that how many different projects are under different weather conditions, and then use this again, pandas command. We've specified pandas before. Get dummies. This is used again and again whenever we use one-hot encoding, and it converts it into this binary format and creates separate fields for these within the dataset. Okay. I create a localized variable environment data, and then we join these. And when you print env data or env data, you get these different fields with the binary information. So that's a byproduct of pd_.getDummies, and then you use .getDummies again here, and you provide the d type as an integer, and you get these binary data fields. This is the magic of one-hot encoding, and I really think that that's quite useful, and I'll show you how I've made use of that later when it comes to classification. So in my larger body of the code, I've specified 2 lists. One is for the weather factors and one is for the environmental factors. Okay, there are 3 environmental factors. Again, you see that here, k-means cluster 3, similar to what we've done before. I'm not going to go into the details of it because we've just covered that in the previous step, but it's very similar setting out to it. But you will find that under the constructor, there are a few more variables, and you'll see why in a second. So I specify those variables here, which is part of the setting out of an OOP platform. Whenever you've got these variables, they have to be specified within the body of the constructor, and then are useful when you are calling out the function using an instance of the class when you invoke the method. I call it invoke because it sounds formal. Okay, so we have environment data preprocessing, which is, or processing, which is this function, uses k-means clustering to analyze the environmental data. Again, I want to see the correlation. I want to see whether a correlation tantamounts to causation in this case. And then another function, weather visualization, which creates a bar plot using a seaborn function, uses the weather facts, which is weather factors that I set out here before, to analyze how many projects were under different weather conditions. So anyone who's looking at this data set, once these functions are invoked, can see this cluster and can see how many different projects were under these different weather conditions. So it's quite useful to get a visceral look into it. Again, very interesting to see how the different clusters have intermediary overlaps but not a combined overlap. Their correlation just doesn't seem to tantamount to causation. Moving on to resource management, I've got different resource fields. In this instance, I used a combined and interactive scatter plot. Well, no, sorry, not an interactive one. I almost spoiled the surprise. I use a static scatter plot. What I want to do is understand how resource management impacts cost. Okay, so we have this class resource management, we have the constructor set out, same process, resource management set out as a localized variable, self.data set out, and then I create a three-dimensional scatter plot, and you'll see why in a second. I set out actual cost, actual duration, and energy consumption. So I want to see how much energy was consumed on projects versus how much money was spent actually, not planned, and then how much time they took. C is, you must have seen that I've used C to define, it's just an industry variable, industry standard template that you use C to define, it could be anything, to define this or to isolate this field from the dataset energy consumption. I set up the C map, that's the unrelated to C, it's the color palette, and then the transparency and the size of the markers, and then the labels, X, Y, and Z axis, because it's three-dimensional, and the title. So when I invoke this function, I see something like this. Of all the visualizations that I've used to analyze the different fields within this large body of code, this one to me seems most intuitive. The reason is this gives me a gradient for the energy consumption. The lightest is the hottest in some ways, the most energy consumed, and the darkest is the least. Now I can look at every project and see that for a project that took somewhere around 700 days, that's this one, that took an actual cost between 6 to 7 million, and this is, even though it says 1 to 7, this 1 E7 means that many number of zeros added to it. That's why it looks like this. And then that consumed very little energy, or least amount of energy, compared to something that sits here that consumed between 12 to 1400 days, that consumed between 5 to 4 million, and consumed close to over 50 grand in terms of energy in kilojoules. This is fantastic when you're presenting energy consumption against cost duration, because almost immediately anyone looking at this can tell that in this data set we are looking at a large number of projects, and there's been an increase in the energy consumption, which may not necessarily be related or directly proportional to the days and the actual cost. But the vast majority are going higher up in energy consumption. And when we're making decisions with regards to environmental impact of projects, especially public infrastructure projects, as is the case with this data set, having something like this is very useful. Right, moving on to the drone data. I went through this quite quickly in terms of created the k-means cluster, because I wanted to see, more importantly, that for the different drone fields, what is the correlation between the different fields. When I invoke this, what I found interesting was absolutely no overlap, no correlation whatsoever between the different between image analysis score, the anomalies that were detected, and completion percentage. Even though this is all part of the drone survey, no correlation between these fields. That was interesting. And finally, risk data. Now with risk, what I've done here is identify the 4 fields that relate to risk. Safety risk score, which is a numeric value, accident count, how many number of accidents happened, crack width, which the higher is, the more risk it is, obviously, and then risk level, which is a separate field already set out in the dataset, high, medium, or low. I set up a class, risk analysis, set up a constructor, and create pair plots, box plots, and scatter plots, some of it using matplotlib, that's the last one, and then I use Seaborn quite a lot within these. First thing I want to understand when I'm looking at risk is immediately what is the relationship between these risk fields? Does one relate to the other? And when I invoke this function and I look at these different risk-related fields, it gives me a very clear understanding of how the different risk-related fields have an impact on the accident. For example, I mean, quite obviously, a project that was high risk had a high accident count. Goes without saying, right? But this gives a very clear indication of it. As I said a minute ago, higher crack width means higher risk. Same principle here, right? And it also gives us a distribution of how many projects were high risk. Quite a lot actually have been high risk, and how many were low risk. It doesn't really look good for American public infrastructure, if I'm being honest. Quite a lot of them are high risk. So this set of visualizations immediately gave me an idea of what I'm looking at in the way of risk. And that's why I felt that this piece of code was extremely important and will inform the analysis that I do with the risk target field later on in this piece of code. Again, a box plot to understand where risk sits, quite high, I'm afraid, and a similar one for this scatter plot. So this was an understanding of the seven analytical fields and the relationship between the different fields. Now we're going to move into the target fields. Structural stability. This is probably the most important, I think, when we're constructing buildings, because we want buildings to be structurally stable. Here I have done some field engineering, and I'll explain why. We have structural stability information as part of this data set. I've covered that in a second. Now, what does structural stability mean? It just means that a building should be able to carry its expected load when it's overcoming seismic loads, when it's overcoming gusty wind. It doesn't develop cracks that compromise its strength. So effectively what it means is that it can resist applied loads and does not have uncontrolled or unexpected vibrations, so low vibration levels, doesn't develop cracks that compromise its strength, that's such as low cracks, small cracks, much smaller than expected, and retains sufficient load-bearing stiffness, so high load-bearing capacity. So that's what we want to see. Now, with these fields that I have available to me, that's vibration level, cracked width, and load-bearing capacity, which are part of my data set, I have created an index, a structural stability index. This is an industry standard. So I haven't invented this, but this is an industry standard. Now, how we do this is you use this formula. K is the scaling constant, and you do a process called normalization, right? Just as we do standard scale, just as we do one-hot encoding, this is again a structural calculation formula. So you've got V is the vibration level, C is cracked width, L is the load-bearing capacity. V max is the limit of the vibration, C max is crack limit widths, and L max is the limit of the load capacity, right? And then normalized value is what we have versus the limit, okay, for all three, and K is the scaling constant. So when we apply these values to this formula, for every single one of those 1000 buildings, you get what is an SSI, Structural Stability Index. So how do we do this? I've got the structural factors set out in a separate list. Class is called structural prediction. We've got the constructor set out. Making SSI is the name of the first method. I create a copy of a local copy of the overall data set. I set out the values of all these max variables, not variables really, these are constants. So limit of the vibration in millimeters per second, that's the maximum that it can be. That's the maximum crack width that we can have, and this is the maximum load capacity, right? And then we calculate the values of the normalizations using indexing, addressing every single one of these fields. So struct factor 0 is the vibration level, that's assessed here. Struct factors 1 is the cracked width, and struct factors 2 is the load-bearing capacity, divided by V max, C max, and L underscore max, okay? And then finally, we create a new field called SSI within this local struct underscore model data set, and that is calculated using this actual formula. And then rounded off to 2 decimal places because I don't want to see 10 decimal places, it's not helpful. This is the body of the code that does the calculation of the structural stability index, and that's why I have commented it out here. I save these changes to the local data set and create another field called stability underscore class. Now you're asking me, why am I doing that? Because these are numeric values and they'll all be slightly different. But I want to give the viewer an immediate understanding of the structural stability proportions within this data set. When you look at 1000 public infrastructure projects in America, how many are structurally stable, how many are not, and how many are high, medium, and all that stuff. So I create a for loop, and for the length of the structural model, that's what we put in the range, right? For index, which is the value, which is a variable in range of the length of the structural model. If the value, you get the SSI for this row. If value is, so we specify what value is, which is it's going to toggle through every single one of the field of the rows in the SSI field. If it's greater than 90 or greater than equal to 90, it's high. So that's high stability, and that will be stored in the stability class field. Remember, we created another one. If it's greater than equal to 25, it's going to be stored in moderate stability, and otherwise, if it's lower than that, low stability. Okay, and then we save that. So that's all created. In the next method, I predict the SSI. So I want to make sure that the dataset that I'm working with has a high accuracy. And for this, I'm going to be using random forest classifier. We did import this as part of the scikit-learn in our very first, before the first step, when we did the imports of all the datasets of the machine learning algorithms, sorry. So capital X and small y, industry standard for creating the training set and the test set. So in X, we are saving the structural related fields and including the SSI and copy of those within X. And in Y, we are saving the stability class, which is what we're trying to predict now. So we divide the data set into training and testing sets. It can be done to a 70-30%. In this instance, that 0.2 means that the test size is 20% and the training size is 80%. That's the split that I've chosen. So training set size is xtrain.shape, and then it prints the samples. Same with training with testing set size. I've used an F string. I find it quite useful when you have to compose large number of a sentence with a number of different variables. I find it useful to all sort of daisy chain them in an F string with curly braces. And CLF will store the random forest classifier with 100 estimators and 42 random state. And then it will fit the random forest classifier to the training data set. And then we will use y_pred, in this case, this variable, to fit or make predictions on the testing set. What we did here, what we fit into CLF, we're going to predict using the x_test. And then we create another variable called accuracy, and we create the accuracy score using y_test and y_predict, which we set out here. So that allows us to print the accuracy of the test set, right? You'll find this wherever I've done accuracy calculations, I've kind of used a similar structure because it tends to lend itself well to prediction of accuracies. And then I sort of print a line for neat presentation. With the structural stability field that I created, I have then created a bar chart for the different structural stability fields. Fairly straightforward template using PX. I think this is Plotly. This is Plotly. Of course it is Plotly, because I wanted it to be interactive, and you'll see in a minute why. Because when you hover over it, it'll be able to give you much more detailed information. And then create a scatter plot to show me the structural stability index. So we're dealing with both stability class and SSI. I've kept the hover data as cracked width because I want anyone who's viewing this to be able to see what the crack width information is for different projects. When I invoke these functions, these methods, you see something like this. Now let's look at the scatter plot first. You'll find that the bubbles are of different sizes. Now why is that? Because when we were specifying this, I specified this line called size. So I specified the size of the bubbles to the vibration level, right? And the color as the stability class. So when you're looking at this, the color for green is for high stability, red is for low stability, and purple is for moderate stability, but the size is for the ones with vibration level. So this outlier here, and I'm calling it an outlier because it seems to set outside the range, has a much lower vibration level of 0.25 versus something here which has a vibration level of 1.51, right? That's why this scatter plot gives quite a lot of information about the different projects and also helps us understand where they are sitting. Seems like a lot of projects are low stability. Yikes, not very good, is it? We had done data accuracy for the training test of 800 samples. Like I said, 80%, 20%, 1,000 different fields, makes sense. Testing test size for 200 samples, and it gives us a prediction accuracy of 0.995, which is very good. But when we look at the stability based on the structural stability class, where we categorized using the for loop, that doesn't look very good for the American public infrastructure. You've got very high number of projects with low stability. Ooh, that's how I reacted when I first saw this. This doesn't look great. But that's why this exercise is important. So we know that this data set is of high accuracy because we just did a test on this. We know it's very high in accuracy, but it's giving us a very grim picture of the overall stability of projects, which is not great. So this is my analysis of the structural stability, which was field 1, where we did a bit of field engineering. We did prediction of the structural stability, we did accuracy testing, and we did scatterplot and both interactive and scatterplots and bar graphs to understand structural stability. The next field is risk. We did a bit of analysis of risk early on. There are 3 risks that are set out in the data set. In this instance, the first thing we've done is categorize the projects by their different risks, created an interactive bar plot using the risk counts index, risk count wise values, color is the risk count index, number of projects by risk level, and specify some plot properties. And we see that we have, again, very high number of projects at high risk. This does not look good. But that's why this exercise is so important, because we can get a lot of data, but this helps us understand what it's saying. That's the first step when we're looking at risk. The next one, we're looking at risk level prediction. We did a structural stability prediction. In this instance, we're going to do a risk level prediction. Pretty similar when it comes to the framework of how we're going to deal with it. The only difference is this is a combination of numeric and categorical features. But what we're going to do is we're going to remove the fields that have no visceral impact on risk. So if we're saying the start date, end date, we're excluding that from risk, we're excluding location and the ID of the project, because project ID is just a sequence number, so it doesn't impact risk. So we're going to put these in an excluded field. We create a local copy of the data frame or the data set in risk underscore model. We drop off in the excluded fields that we defined here and created a separate variable for here. This gets invoked when you're invoking the function. So when you create an instance for the class, you specify the values with the variables with the exact same name. You specify them before the class is defined, and that allows the variables to get imported and then invoked. So we drop all the columns from this list, and then we print the excluded fields, right? Again, we create a testing and training set. We drop risk level from the data set and assign it to the y and small y, which is the target field. So large X is the training set and y is the target field. And categorical underscore columns, where we select the categorical columns. So because this is a combination of numeric and categorical data, that's why it's important to differentiate them out. So select underscore data D types is used to define or isolate the data type based on what we specify here. So there was an instance previously where we specified that as number. So when it was number, then the variable mentioned before would only hold the numeric values. But when it's specified as object, it's holding the categorical values, right? And then once we have isolated them, we specify to the user that these are the categorical columns we are encoding. And I showed you one hot encoding as part of this code. So we're using get underscore dummies, same principle, same structure. Columns stores this information, and within the X variable, we apply one hot encoding. Before and after, we show them the risk categories, and then split the data into training and testing sets. Same principle, same 80%, 20% split, and apply random forest classify with the same values. So we're using it like for like, fitting the random forest classifier to the training model, making predictions on the testing set, and saving it into y_pred. Now we can use the same variable name because it's specified inside the class, so we're okay there. And calculating accuracy using accuracy_score, because we want to see whether or not the information that we've been given in the dataset is accurate. So as we printed on excluded fields, we get the excluded fields, we get the categorical columns we need to encode, shape of the features after the encoding, risk categories, high, medium, and low, testing set, training set, and prediction accuracy in this case is 0.935. Okay, slightly lower than the structural one, but still fairly high. So we know that this is a reliable data set. Then we look at accident counts against the safety risk score versus the crack widths. How do these affect the accident counts? And for the purposes of this exercise, I use an interactive scatter plot, and I'll show you in a second why that is. So we have a risk management class, a constructor, a safety management method, in which using the color and the size, I can visualize how many accidents happened on a range and assess the functions. And unfortunately, the fact that these are all higher on the yellows and oranges bodes that a lot of projects have had a high number of accidents. Okay, the purple is the lower, so you're going down on the accident count, and the higher number of accidents have had higher cracked widths. I think we observed that when we were looking at the plots, when we initially looked at risk, and we looked at I'm gonna go back, looked at these plots, so we could understand that, yeah, higher cracked widths, high accident counts means higher risks. So we also get a more clear understanding of the impact they have on the accident counts, and this is important when you are building, constructing, or funding projects, because we don't want accidents on our projects. So this is how we understand the impact of risk on accidents. And now we're coming to step 8, which is the last step in this exercise, cost. If you've stuck around so far, thank you. Let's look at how we predict cost overruns. The most important thing, as far as I'm concerned, I come run into this again and again. Cost overrun is effectively overspend. If we can predict how much overspend or what kind of overspend, that would be great. So we target cost overrun, which is the target field here. We create a large class for it, create a constructor, specify the target field within this localized variable, and then we create a separate method that says cost_over_pred. Okay. Again, X defines the dataset without the target column, Y defines just the target column. So wherever we've used these two variables, we've used X to contain a large amount of data, but not the target field, and Y is often, a small y is often the target field. I'm not sure why, but this seems to be a Python coding standard, so I've just run with it. Categorical columns encode the categorical information from this data set. Numeric keeps numeric 1. We run standard scalar. I explained what that is earlier on and saved it into numeric transformer, and then we run a one hot encoder and save it into categorical transformer. And then we pre-process them into a column transformer variable through a column transformer function. Transformers is equal to then numeric values and categorical values. This is so we can feed this into the model later. So what we're doing here effectively is creating a model pipeline. Now, if you remember, when we imported my machine learning algorithms, we imported this particular scikit-learn algorithm. This is where we have used this later on in this risk field. That's why it was important. So moving on from there, we have used the pipeline function. Again, like I said, we've just imported it. And that's why it's useful, because it helps us condense what would be a very complex function into a very short number of steps. Random forest regressor using standard depths and branches, or standard number of steps that we want to include within this. Splitting the data set, fitting the data set, fitting the model using the trained data, predicting for unseen data, and then printing the output. So here we are calculating the feature names. Basically what we're doing here is doing a list of the most important fields with an impact on cost in a descending order and calculating accuracy. Okay, so we've already done predictions on the test. We isolate the importances within using feature underscore importances, gives an importance score for every feature, and using pd.dataframe combines the two loss lists into a smaller data frame and sorts it by descending order. Ascending is equal to false means it sorts it by descending order. And then we print them using an f string. I specified that I seem to like them. And then we visualize them into a static scatter plot. And the final step in this code is using mean absolute error and R2 score to calculate the accuracy and performance of this data. Mean absolute, when you're looking at mean absolute error, it's the average of the absolute differences between sort of the predicted and the actual results, right? So you're checking the accuracy of your prediction model. And R square score is like, it's a statistical measure. So gives a proportion of the variance in some ways. These are useful metrics to understand the accuracy and the performance of the model, and usually the higher value means the better they're performing. So we calculate those, and then we look at the cost correlations, which is a fairly short method to look at how these values relate with each other. The end result, as you can see, as I mentioned, that there's going to be a list of the top 10 most important features affecting cost. Naturally, actual cost is at the top of it, planned cost is next. Interestingly, the very next is labor hours. We talked about importance of resource, and labor is a resource. And interestingly for me, when I looked at this, material usage was at the bottom of the list, and this is kind of contrary to industry perceptions that material expense, amounts to a large percentage of cost wastage. Apparently not, at least not in America. We've done a scatter plot which shows the predicted cost versus actual cost. Here, this dashed red line is your, it's like the perfect prediction where the actual cost has met the predicted cost. And as you can see projects where that actual cost has met the predicted cost. There's not that many, but you can see some of them there. And then a lot of them are on the outside, with one or two being outliers. So we get a value of the mean absolute error and R square score, as well as a list of the correlation factors with the value of their correlation to cost overruns. So this was the final step of the Computing for AI Assessment 1 video manual. Apologies, this took a bit longer than I had expected, but thank you for sticking around and watching all of it. As I said earlier, I'm going to put timestamps in the description of this video. So if you want to jump to a specific section to look at it again, or just look at a particular section, please feel free to do so. And thank you for watching.